Alrighty, so today we're going to talk about section 6.4, the Fundamental Theorem of Calculus. Love my emphasis there on that, my dramatization of it. The Fundamental Theorem of Calculus. This is it. This is like the biggest theorem of them all in calculus. Today we will finally talk about how to do a definite integral analytically and find that exact area underneath the curve. There's two parts to this theorem though, and we're going to talk about part one first obviously. But it says if f is continuous, on AB, then the function capital F of x is equal to the integral from a to x f of t dt has a derivative at every point x in AB and df dx, where I'm d capital F there, is equal to the derivative with respect to x of the integral from a to x f of t dt, and all of that is equal to little f of x. So basically what we're saying here is that if I take the derivative with respect to x of an integral where I have a lower bound of a, upper bound of x in this instance, when I derive that integral, I'm just simply going to get the function, the integrand back with x plugged into it. Essentially what this is saying is that derivatives and integrals, definite integrals, are basically opposites of each other. Those operations cancel each other out and I just end up back with the integrand, but with my variable x plugged into it. So we can actually use this to solve problems. They love asking questions on the AP Calculus exam with the fundamental theorem. So I can ask you, for example, to find dy dx, and they'll look like a derivative question. Find dy dx if y is equal to the integral from negative pi to x cosine t dt. By the part one of the fundamental theorem, I'm deriving this integral. A is A in this case in the theorem, A is just a constant. Negative pi is our A value here for this one. My top bound is x, so this is going to simply give me cosine of x by that first part of the fundamental theorem. I'm simply getting the integrand back with x plugged into it instead of t. Well, what if it's not x? Because a lot of times it won't be. What if it's something else though and it has x in it? What if we wanted to find dy dx Now, if y is equal to, this is almost the same thing, the integral from negative pi to x squared. cosine t dt. So now if we want to find the integral from negative pi to x squared, we are going to basically end up with, when we derive that, we are still going to end up with cosine of, now we'll have x squared plug in instead of x. But the one difference is that I have to multiply by the derivative of the inside. This will make more sense once we talk about part 2 of the theorem, okay? And I really don't, I actually kind of don't like how they put this as part 1 and that as part 2, but I kind of understand why, but still it doesn't really flow very well. But you have to multiply by the derivative of the inside function right there. X squared is my inside function, so I have to multiply by the derivative of that, which is 2x. That's the chain rule. It is essentially the chain rule that I'm having to use right there. This will make a little more sense once we talk about part 2. So if it's something else besides x, you'll have to do that. Also, you can use your properties from yesterday's Ed puzzle video. So if instead I wanted to find dy dx, if y is equal to the integral from x to pi cosine t dt. If my x is on the bottom instead of on the top, my constant now is on top, I can just simply rewrite that as negative the integral from pi to x. I can flip the bounds and just put a negative in front, cosine t dt. And now I can derive this with respect to x. And I'm just going to simply get negative cosine x. My x is on the bottom. All I do is I flip it. That negative is just a constant multiple. So I just apply the rule here, and I get negative cosine x in this instance. Okay, it just changes, so you can flip bounds if your x is on the bottom on the wrong side. All right, that's part 1 of the fundamental theorem. Here's part 2. This is the real big one, the big part, how we're going to do definite integrals analytically. Without having to use the calculator, without having to use the numerical integral on the calculator, how can I calculate a definite integral to an exact amount by hand? Part 2. I'm going to do dot, 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 meaning I'm continuing everything from the part 1. So we're still talking about little f being continuous on AB and the function capital F of x, blah, 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 blah. But then the integral from A to B of little f of x dx is equal to capital F of B minus capital F of A, where capital F is any antiderivative of little f on the interval A to B. So to do a definite integral by hand, we antiderive the integrand. We antiderive little f of x, get capital F of x. We plug in the top bound, we plug in the bottom bound, and we subtract those values. That's how you find the area exactly underneath the curve on a given interval. Antiderive. Example. Let's do the definite integral from -1 to 3 of x cubed plus 1 dx. let's antiderive x cubed plus 1. So x cubed, I add 1 to the power, divide by the new power. Antiderive 1, I get x. Because x's derivative is 1. So 1's antiderivative is x. Now, normally we would pick up a constant here. And I'm going to go ahead and throw it in here, but I'm going to show you what happens. So we'll antiderive, and then I'm going to draw this line right here, and I'm going to put my bounds on either end. From 3, -1. And then on the next step, what I'm going to do is I'm going to subtract. I'm going to plug in 3, get an answer. I'm going to plug in -1, I'm going to get an answer. Okay? I'm putting the plus c here for right now, but I'm going to show you that it's not necessary. So I'm going to do 3 to the 4th divided by 4 plus 3 plus c, get an answer, and then I'm going to, over here, I'm going to do -1 raised to the 4th divided by 4 plus -1 plus c. We're going to subtract our answers. Now notice I'm going to end up having c minus c. The constant's going to cancel itself out. On definite integrals, you do not have to worry about putting the plus c. I know when we anti-derived before, you put the plus c, and I'd rather you put the plus c and realize that it's going to subtract out than to not put the plus c later on when we do indefinite integrals in the next chapter. Yes, there is a such thing. Okay? So, we will need the plus c in the next chapter for sure. 3 to the 4th, that's 3 times 3, which is 9 times 3 times 3, that's 9 times 9, basically, which is 81. So that gives me 81 over 4 plus 3 I'm losing the c, by the way, because those are going to cancel each other out. -1 to the 4th is +1 divided by 4 plus a -1. And 81 over 4 plus 3 gives me 93 over 4. Check that. I'm going to double check just to make sure it is, 9 o'clock in the morning and I'm trying to do mental math, Just want to make sure. 81 over 4 plus 3 is 93 over 4, yes. Minus 1/4 minus 1, basically 1/4 plus -1 is the same thing as 1/4 minus 1. That's going to give me a -3/4. This is going to end up being minus a minus, makes that a plus. And I'm going to end up with 96 over 4, which is 24. So the exact area under the curve, x cubed plus 1, from -1 to 3 is 24. You could confirm that with the numerical integral and see that it works out like that. All right, one more example. Let's do the integral from -pi to pi over 2 of cosine x dx. Maybe we'll do a couple more examples just to make sure we're good. So I anti-derive cosine, I get sine. Sine of x, I'm going to plug in pi over 2. I'm going to plug in -pi, and I'm going to subtract. Sine of pi over 2, sine's the y coordinate, that's 1. So that's going to be sine of pi over 2 minus the sine of negative pi. This is 1 minus sine of negative pi. The y-coordinate at negative pi is 0. So that's 1 minus 0. So the answer is 1. Now, let me talk a little bit of why this makes sense now in terms of back here. Back here on this example, let's back up to this example right here where we had to use the chain rule. If we just look at this definite integral first by itself, I'm going to take an anti-derived cosine to get sine, and I'm going to plug in the top bound and the bottom bound. So I'm going to have sine of x squared minus sine of negative pi, right? Using part 2. If I was to anti-derive this, all right? So again, what that would equal is the derivative with respect to x of sine of x squared minus sine of negative pi. I'm still deriving that, but now I'm going to derive this. We just used part 2, plug in our top bound, plug in our bottom bound into our antiderivative, and subtract. If I derive this, sine of negative pi is a constant, so all that's going to go to 0. That term's going to go to 0. That's why the bottom bound doesn't really matter as much. Okay? But the top bound, with x squared plugged in it, I'm going to derive that. Well, if I derive sine of x squared, that's an x squared function plugged into a sine function. I have to use the chain rule. That's why we use the chain rule here with that. Okay. Now I can ask you to anti-derive a whole lot of different types of functions, reviewing your derivative rules. What if the bounds, one more example, what if the bounds are both x? Okay, this will be back to kind of part 1, but we'll marinate in a little bit of part 2 here as well. What if instead I want to find the derivative with respect to x of the integral from x squared to x cubed of sine of 2t dt. Okay, bottom bound's x squared, top bound's x cubed. If we want to analytically solve this, we're going to have to break this down into 2 separate integrals. We're going to have to use our integral properties that we talked about yesterday to help us do that. Well, not necessarily. We actually don't have to necessarily. We can break it down into two separate ones. But if it has bounds of both of these, that simply means that when we go in here and we anti-derive this, right? So we're still doing the derivative with respect to x of, we'll do this with part 2, even though we're still thinking about part 1 as a shortcut. We anti-derive sine, we get negative cosine, right? Of 2t but we're actually, instead of using t, we're actually going to plug in our bounds, right? We're going to plug in our top bound, our bottom bound, we're going to subtract. So we're going to plug in x cubed, and we're going to subtract negative cosine of 2x squared. Sorry, ran out of room there with my parentheses. Well, when I take the derivative of these, I'm going to get positive signs again, basically. Right? Because I'm going to end up undoing what I just did with the anti-deriving, basically. So, but I have to also take the derivative of the inside function. So I have to take the derivative of 2x cubed, I get 6x squared. Minus, again, I get a positive sign, but I have to take the derivative of the inside function, which is 4x, times the sine of 2x squared. I forgot something. I know what it is, too. Right here, when we anti-derive this, because the derivative, the inside has a 2t, I have to divide. It's like the reverse chain rule. I have to divide by the derivative of the inside. So each one of these is going to be divided by 2. So that's going to reduce this down to 3x squared sine of 2x cubed minus 2x sine of 2x squared. Now, I'm going to show you, connecting this back to part 1, I'm going to show you how this would have been a lot easier. Using part 1, we would have simply, if we just did this with part 1, we didn't think about part 2, this would have been a whole lot easier. If I just simply plugged in the top bound, plugged in the bottom bound, and subtracted into that function right there, but multiply by the derivative of these functions that I'm plugging in, these inside functions, x cubed and x squared, I would have gotten 3x squared sine of 2x cubed, so that's x cubed been plugged into that function right there, minus derivative of x squared is 2x times the sine of 2x squared plugged into that function. And I would have gotten this answer in the first place, just using part 1. And that would be my answer to that. Okay. All right, hopefully this has been good. Hopefully this makes sense. Let me know if you have any questions, email me. I'll assign some problems to go with this. Thank you all.